Beneath our feet lies a hidden world, one that stretches miles into the Earth's crust, beyond the reach of sunlight, beyond what we once thought possible for life. A place of extremes, where life defies the impossible. From ancient microbes surviving for millions of years, to bizarre organisms thriving without sunlight. This underground world is rewriting the very definition of life on Earth. A vast, alien-like ecosystem thriving in extreme heat, crushing pressure, and total darkness. Here, ancient microbes feast on minerals, strange organisms survive without oxygen, and life endures in ways that defy the rules of biology. Welcome to Earth's deep biome. I'm James Stewart and you're watching Astrum Earth. In this video we'll uncover the secrets this underground biosphere holds, what sorts of organisms we can find there, the challenges they face, and what this could all mean for how we think of life not just on our planet, but on other planets too. It's time to go deeper and uncover the mysteries of this unseen world. So where exactly is this unseen world? This is a region that extends down to at least 5 kilometers below the land and 10 kilometers below the seabed. This deeply buried environment might not seem like a very hospitable abode for life compared to a tropical rainforest. In fact, not even compared to a parched desert or frigid glacier. But scientists think that the deep biosphere could host as much as 15% of all the biomass on the planet. You've heard about extraterrestrial life, but we're uncovering the eerie diversity of intraterrestrial life. The biosphere, comprising everything from the mightiest giant redwoods down to the tiniest microbes and viruses, was once thought to end not too far beneath our feet. Of course, scientists knew about creatures that spend their whole lives in deep caves or that creep, crawl and burrow through the soil. But all life was understood to take its energy directly or indirectly from the sun, either through photosynthesis or consumption along the food chain, meaning nothing could stray too far from the light of day. But as prospectors began to sink mines and boreholes deep into the ground in the early part of the 20th century, we started to question that assumption. Fluids extracted from deep in the bedrock contained chemicals that seemed to have a biological origin, and some scientists were able to cultivate bacteria that appeared to have been residing far below the surface. At first, researchers couldn't be certain that the life that they were detecting in these boreholes hadn't been introduced from above by the act of drilling itself. There's not generally a need for drilling equipment to be sterilised, after all. However, as scientists developed techniques to avoid contamination from the surface, they found that living cells were found in nearly all the samples that they brought up. Wherever there were cracks or pore spaces through which water could percolate, there was life. We know how different life can look if you go just a little deeper below the surface, into caves and underground burrows. Strange adaptations start to emerge, like the creepy eyeless face of the Mexican tetra, or the hairless naked mole rat. But we're delving even deeper, to the sediments at the bottom of the ocean and deep into the Earth's crust. What kind of life can we expect to find there? And what is it like? All living things can be divided into 3 domains: bacteria, archaea, and eukarya. This idea was proposed by American microbiologist Carl Woese in 1990 and helps us to understand the major branching points in the tree of life throughout the course of evolution. Most of the life you'll be familiar with, including us, belong to the eukarya. We know what bacteria are, but what about archaea? Like bacteria, they are single-celled, but they resemble some of the earliest life forms on Earth with a unique kind of cell wall and genetic makeup. Archaea thrive alongside bacteria in the deep biosphere, As smaller unicellular organisms, they're often better at coping with tough environments, whether that's extreme temperatures, high pressure, or scarce nutrients. There's no question that the deep biome is a difficult place to live. So with this in mind, let's take a look at some of the most major findings from our journeys below the surface. And if you're tired of your major online findings seemingly coming to the surface through Google searches revealing your old home address, your mum's name, and your favourite sandwich order from 2012, we've got something that can help. Yep, all that information being available is thanks to data brokers, companies that collect and sell your personal info like it's Pokemon cards. That's why I started using Delete Me. They find your data on hundreds of shady websites and remove it. I'm talking names, numbers, relatives, gone. A digital spring clean all year round. I personally use Delete Me to protect myself from stuff like identity theft, phishing scams, or some rando figuring out where I live because I once posted about oat milk. You can get 20% off with my link joindeleteme.com/AstrumEarth and use code AstrumEarth at checkout. Thanks to Delete Me for sponsoring this video. Links in the description if you want your digital life a little more private. In the marine world, researchers dabbled in shallow core sampling of ocean sediment throughout the 20th century, and were shocked to find that cells were present and detectable at all depths that could be sampled. This was our first piece of evidence that life could exist in old sediments, some of which were thought to have been deposited more than 1 million years ago. Then began a significant phase of ocean drilling, known as the Ocean Drilling Programme, from 1983 to 2003, which gathered lots of data on the ocean's deep sediments. And with this data came another big shock for the scientific community. That in fact most bacteria and archaea may be found in deeply buried sediments. This finding prompted new waves of deep biome exploration that continue to this day. In 1976, scientists towing specialised cameras along the sea floor made the discovery of deep sea hydrothermal vents. These vents are ancient geological structures that spew out a kind of hot chemical soup, rich in minerals and other nutrients. Upon later visits to these vents in submersibles, scientists were met by an unexpectedly rich and vibrant community of life. So they started to think of these smoking structures as a window to the deep biosphere, and they weren't wrong. These creatures were definitely not something you'd find on the surface. In fact, some vents host microbes that can function at the boiling temperature of 100 degrees. Discoveries like these push the limits of life beyond what we thought was possible. And as a result, many microbiologists now think the highest temperature at which cells can function may be closer to 150 degrees. But as well as extreme temperatures, organisms living near hydrothermal vents must cope with intense amounts of pressure. The atmospheric pressure at sea level is 0.1 megapascals. The average depth of the ocean, where deep sea vents would be found, is 3,800 meters, or 38 megapascals. Pressure 380 times greater than you'd experience at the sea surface. To survive here, you'd probably have to be what scientists call piezophilic, or pressure-loving, like the deep sea bacterium Photobacterium profundum SS9. Not the catchiest name, but this species has been adopted as somewhat of a model organism to understand deep sea bacteria as a group, and was originally discovered in the Philippines at a depth of 2,500 meters. P. profundum can withstand pressures from 0.1 to 90 megapascals, so it can be taken from the bottom of the ocean and cultured at the surface for scientists to study it. And the results of these studies? Well, scientists found genes that allow this bacterium to repair DNA damages caused by high pressures, and it's actually lower pressures, like those found at the sea surface, that activate this species' stress response. This is proof that P. profundum isn't just tolerating high pressures, but actually prefers them. At immense depths like these, the extreme conditions, lack of sunlight, and primitive nutrients can really affect the way you live. For organisms in subsea floor environments, the best and sometimes only strategy is to slow right down. What does this mean? When energy is scarce, all your metabolic processes slow down, and the little energy you do have is probably being used to repair yourself, instead of dividing and reproducing. Scientists have found organisms below the sea floor with incredibly long lifespans, surviving in a kind of metabolic stasis with little movement or change. Microbes living in seafloor sediments are slowly buried over time as more sediment and other organic matter is deposited on top of them. This means the further down into seafloor sediments you go, the older the microbial communities become. With this information, scientists can estimate the number of generations that have passed since the microbes were first buried, and the results are pretty amazing. Researchers estimated that for a site in Peru, a microbial community at 40 meters below the sea floor had passed through around 11,500 generations. It takes around 4 million years for sediment to reach that depth, so a simple calculation tells us that the average generation for these microbes lasts for nearly 350 years. If you compare that to E. coli, which has a generation time of just 20 minutes, you can understand just how slow life is when you live at the bottom of the sea. These life forms exist on geological timescales, so it's no wonder they don't look like they're doing much. But if you shift your perspective just a bit, you realise that this is still a complex and dynamic world where communities respond to tectonic shifts and geophysical forces on continental scales. So, we know that each generation of these microbes likes to hang around for a long time. But how do they manage this? The thing that surprises scientists the most about these organisms is just how little energy they can survive on. We humans use about 100 joules of energy every second to fuel our bodily functions, which is roughly the energy it takes to power a ceiling fan. But in a recent paper published in Science Advances, scientists calculated that the average microbe living in the ocean's deep biosphere uses 50 billion times less energy than a human. Talk about energy conservation. Things don't stop underwater, however. As we go about our daily lives on the surface, miracles are also happening deep below the surface too. Within the Earth's crust, it's often in the waters of deep fractures where we find microbes. Against the odds, these microbes are metabolically active, but again at slower rates than life on the surface. They're often scrounging around for scraps, surviving on organic matter that's buried within deep sediments or travels through groundwater stores to meet them. As you'd expect, these aren't the best energy sources, but it's enough for some life to survive. However, as you go even deeper into the bedrock, even these sources become scarce. At the ultimate level of deep biome survival, organisms can only make use of hydrogen gas generated as a byproduct of the interaction between water and rock. Here, cell numbers can be as low as 10 cells per milliliter. But strangely, despite working with so little resources, these deep biome populations still have a small degree of diversity. In fact, the difference in species composition between the organic carbon-fed and hydrogen gas-fed biospheres is quite impressive, with each species having its own unique way of surviving down there. Just like the oceans, we've discovered some amazing species in the continental deep biome. In one expedition to a South African platinum mine, researchers discovered a whole new shape of bacteria that was previously unknown to science. They looked like an ordinary rod-shaped species, until a cross-section revealed not a triangle, not a square, but a star. These stellar life forms are just 1/10 the width of a human hair, but their shape is designed to maximise the amount of nutrients they can absorb, which is vital when you live in such a depleted environment as this one. So far, we've mainly focused on bacteria and archaea in the deep biome, and although these groups may be more common in subsurface environments, recent studies have also started to uncover the eukaryotes that are also braving this extreme lifestyle. Dr. Henrik Drake and his colleagues presented the first in situ finding of fungi in crystalline rock in 2017, at a depth of 740 meters. And in 2011, scientists analysing water extracted from rock fractures in a South African gold mine even found multicellular life. That water had been sitting 3.6 kilometres below the surface for at least 3,000 years. And in it, the researchers found minuscule worms called nematodes, including a species that was previously unknown to science. They called it H. Mephisto, after Mephistopheles, the devil that loves not the light from Dr. Faustus, which does seem pretty fitting for a species that lives 1.3 kilometres deep in the Earth's crust. There's a lot to unpack there. We've dealt with incredibly energy efficient microbes loving life in Earth's pressure cooker, entirely new shapes of bacteria, environments with only hydrogen gas to eat, and even a species named after the devil. Earth's deep biome has certainly delivered so far. So how do you even begin to go about measuring something that's underground and quite literally everywhere? Whilst it's tricky to pinpoint a specific number for how much deep biome life is out there, we do have a pretty good estimate. A recent paper from the Deep Carbon Observatory in 2018 reviewed around 3,800 measurements of cell concentration worldwide. Staggeringly, they calculated there are between 200 and 600 octillion cells in the continental subsurface alone. Well, okay, what does that mean? Well, there's an estimated 30 trillion cells in your body, so the number of cells in the continental deep biome is 20 quadrillion times more than that. Do bear in mind this doesn't include sub-seafloor sediments or groundwater stores though. Deep biome life is thought to occupy a volume ranging from 2 to 2.3 billion cubic kilometres, which is almost twice the volume of all the world's oceans. And since we estimate that we've only explored 5% of the world's oceans so far, just think how much of the deep biome remains untouched. Now we know there's a lot of deep biome life out there, thankfully, there's a global project to categorise it into the future. The Census of Deep Life involves DCO and other partners, and its goal is to perform a global survey of life in continental and marine subsurface environments using deep DNA sequencing technology. Throughout this project, researchers are hoping to uncover the genetic diversity of subsurface life, their community structure, their role in carbon cycles, and much more. They may even find out whether there are any keystone species for the deep biosphere. Keystone species are essential for the survival of other species in an ecosystem and are often good indicators of ecosystem health. You may have heard how beavers build dams that allow other animals like fish and amphibians to thrive, or that looking at the lichens growing on a tree can tell you about air quality. Well, we might find a similar species or group in the deep biosphere. If it exists, it would probably be a pioneer in colonising the deep biome, helping to turn it into a place where other microbes can thrive. Scientists are already eyeing some bacterial orders that might be good contenders because of their metabolic plasticity and their presence in many of the deep microbiomes we've studied so far. We're not there yet, but answering some of these questions would give us a better understanding of how these habitats come to be colonised in the first place, and what a healthy deep biome looks like. Perhaps though, despite all of that, one of the most exciting parts of this entire concept is that it may not be limited to just planet Earth. All of those discoveries of intraterrestrial life to date does beg the question, could this kind of life exist outside of our planet? It seems like wishful thinking to imagine alien coral reefs or Amazon rainforests, but an alien deep biome might be more realistic. Lots of the debate around this topic was sparked by a paper published over 30 years ago, so let's dive into some of its claims. In 1992, astrophysicist Tom Gold published a landmark paper called The Deep Hot Biosphere. In it, he argued that microbial life is probably as widespread through the Earth's subsurface as it is on the surface, but that the rules are pretty different. Chemical sources of energy rule over photosynthetic ones, and temperature is the limiting factor for survival as you go deeper into the Earth's crust. As we've heard from our examples of deep biome life, Gold wasn't far off from the truth. But it was his comments about life on other planets that really got people talking. We sadly know the other planetary bodies in our solar system don't have the right conditions for surface life, but Gold wondered whether the same could be said for subsurface life. We Earth lifeforms can be grateful for our planet's status as a Goldilocks planet, warm but not too warm, so that liquid water can exist on its surface. In this respect, Earth is unique among the solar system's planets and moons. However, conditions in the deep biome tend to be more consistent, and this could be true for planets besides Earth. Although we can't find surface water on the planets and moons in our solar system, that doesn't mean there's no trace of it at all. In fact, scientists think that at one point, 1/5 of Mars was underwater. We have a great video on the Astrum main channel that goes into more depth on this, do check it out. And some moons, like Jupiter's Europa or Saturn's Enceladus, have subsurface oceans beneath their icy exterior, which make themselves known in explosive plumes. What's crazy is that NASA have even detected organic matter in the plumes from Enceladus, with potential to be the first building blocks for life. It's often said, on Earth at least, water means life. So it's within reason to suggest that the same could be true for other planets too. With water present, you may get similar water-rock interactions to those observed on Earth, producing hydrogen or some other geogas that subsurface life would need to use as an energy source. So although surface conditions may seem too harsh to host extraterrestrial microbes, they could be hiding just out of view in the deep biomes of their home planets. Intraterrestrials, if you like. As our journey beneath the surface comes to an end, I'm quite grateful to be a surface dweller. Many scientists say that exploring the deep subsurface is like exploring the Amazon rainforest. And I'd go a step further even and say it's like exploring a whole nother world. Although we're not even close to exploring the whole of the deep biome, we've seen bacteria that can withstand insanely high pressures, boiling temperatures, and environments with only hydrogen gas to eat. Conditions so extreme that, like H. Mephisto, you can share a name with the devil just for being able to survive there. Scientists have been fascinated with this world ever since we could first drill into the ground or explore the oceans, and it's possible that learning about our deep biomes will give us a better idea of what's going on beyond Earth's reach. Gold famously said his ideas would have gotten him burned at the stake in a different time, but it seems like now is the perfect time to start exploring them. In doing so, we may realise that the deep, hot biosphere is the norm rather than the exception for planets across the universe.